Hello everyone, my name is Elisa Baum and I am Percona's Director of Product Marketing. We'll begin in just a moment, but first I'd like to conduct just a little bit of house cleaning. First, please raise your hand using the hand icon located in the GoToWebinar control panel to let me know that you can hear me all right. And let me see. Okay, great. I see a bunch of hands. Thank you very much. Next, during this webinar, you will be on mute. Should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we'll take time to answer as many questions as possible, and those that aren't addressed will be answered in a follow-up blog entry on Percona's MySQL Performance blog. In addition, a recording of this webinar will be made available to everyone within 48 hours. I'd like to thank you for attending today's webinar, MySQL Indexing, Best Practices for MySQL 5.6, presented by Percona CEO and founder Peter Zaitsev. In addition, Matt Griffin, who is Percona's Director of Product Management, will be joining Peter for the questions and answers part of the show. And with that said, I'd like to turn the floor over to Peter. Go ahead, Peter.
Hey, thank you, Lisa. So we're going to talk about MySQL indexing best practices, and we'll specifically focus on some changes in MySQL 5.6. Now, I would say what I believe you did a very good choice coming out to this presentation, because really indexing is a skill which is crucial both for knowledge for MySQL development and DBA, and also poor index choices are responsible for very large number of production problems. We very commonly see missing index can be cause of their downtime or very severe performance problems. And as much as it is very a serious issue, indexing is not really rocket science, at least the basics of it. And if you just digest what you learned today in this presentation, I believe you will be in a top 5% of your DBAs or developers when it comes to understanding of the MySQL indexing. So in this presentation today, we will look at three main topics as related to indexes. First one will cover understanding indexes, how indexes work internally. Then we'll look at the approach you can use to set up indexing for your applications, and then we'll look at working around some common MySQL limitation when it comes to the ability to use indexes. First, let's think about indexes and what are the indexes in the nutshell, right? And indexes really is a database structure which is created entirely to speed up access to a database, to make our queries run faster. So if you take your database and go ahead and drop all the indexes out there and then run some select query, any of select queries you're running will still be able to run, but it may not be able to complete in your lifetime. Now, indexes also help us to enforce a constraint of primary key indexes, foreign keys, but these are really conceptual different data structures which are just typically implemented using indexes. Now, there are a number of indexes which exist in the wild. There are B+Tree indexes, which is the most common index type and which we will focus our attention for. These are R-tree indexes in MySQL, which are used for dealing with GIS data, which have been commonly MySum only, but which are also being implemented for Innodb tables for MySQL 5.7. So I'm sure we'll look more of those index types. There are hash indexes which exist in memory and NDB tables, which are a very good choice for point lookup queries. And there are also full text search indexes which are helpful to optimize our full text search natural language search queries which exist for MySum tables and Innodb indexes starting with MySQL 5.6. As you see, there are a whole bunch of indexes which exist out there. The good thing is, as a DBA or developers, I believe more than 90% of your time will be focused on working with the B+Tree indexes, and this is what we are going to focus on for this presentation. Now, when we refer to B+Tree indexes, such as if you create an index with MySQL with type B+Tree, we are really speaking about a family of different types of implementation which all share similar attributes. They are similar to B+Trees, right, to true B+Trees. Depending on the storage engine, we may be looking at the B+Tree indexes, B+Trees, T-trees in NDB storage engines, or red-black trees for in-memory storage engine. Now, what is important to know from the practical implications, what kind of queries those indexes can and cannot optimize, they behave essentially the same. That is why they're all using the same B+Tree name when you create an index. This is an example of an index, and here I in particular use B+Tree example because this is what Innodb, the most commonly used storage engine, uses. As you can see, B+Tree has essentially tree-like structure, which has a different structure for its branch nodes or root node and the leaf nodes. The difference here comes with our branch nodes and root node contains pointer to other pages, while the leaf nodes has a data pointers, or as in case of Innodb primary key, it can contain the data. As you can see in this case, we would essentially have multiple pointers going from our root page to the branch and then leaf pages, which allow us to find any data using their descent in the tree. What we also see in this tree is the pointer from a leaf nodes from one to the next one, which is an important optimization which allows us to do the range scans in the B+Tree indexes without necessarily having to go back up the tree and go back again. What is interesting for Innodb tables in particular, what we actually have a pointer between their leaf node pages following in both directions, both forward and back. That means Innodb tables are optimized for range scans both in forward and reverse order the same way. Finally, if you would note on those 3 pages or 4 pages which are displayed here, you can note what some of them contain 3 values and some only 2. This is to illustrate the reality of B+Trees, what they would have often a free space in them. And that's indeed somewhere between 25 to up to 50% of space may be free in their B+Tree index pages, where some data can be added without restriction the tree. In reality, of course, B+Tree use pages which are significantly larger than displayed here. So for a typical index, you may be looking for hundreds, in some cases maybe even as much as thousands of elements stored on a single Innodb page. Right? What that means is the number of levels in a B+Tree is not very large in most cases. Now, when we look at the indexes for MySum and Innodb tables, they are a little bit different. In MySum, data pointers point to physical offsets in a data file, so all the indexes are essentially equivalent, whether that's a primary key, unique key, or secondary keys, they are all the same in how it behaves. In Innodb, there is a primary key, either implicit, which was created for you, or explicit, which you created manually, is special because it stores data in the leaf pages, not a pointer to the data. And then the secondary index, they store primary key as a data pointer. Now, as we got some understanding about the index, let's think about what kind of operation, what kind of, let's say, a simple where clauses our B+Tree index can optimize from a point of lookup. First is point lookup, right, or equality constraint, right, when you look at for everything which contains key equals a certain value. Then we can look at the ranges which are open from one side, like something with a key more than 5, or closed range where key belongs to the range between certain two values. These are essentially the most important types of the B+Tree index can optimize. Now there are some things where B+Tree index cannot really help us. So for example, if we want to look at the all rows where last digit of the key is 0, right, or the last letter of a name is A, indexes, B+Tree indexes cannot help us to find this data faster because it cannot be really defined as any kind of range operations. Now, when we speak about strings, they work really very similar to the numbers because we can take a look at the strings and define a sort order within them, which is called in MySQL words as a collation. With different languages, the sort rules may be different, and that's called the collation is being different. And this defines a sort order within the strings which is needed for us to create an index. What is also special for strings is what we can have in like operator. And like operator with a fixed prefix actually is changed internally to be some sort of range, and that can be optimized quite well. It is like with fixed suffix, but with percentage sign, right, or underscore at the start. That is what cannot be optimized well. And this is like one of the nastiest queries you can run into when you do like percent, then certain search string, certain keyword, and then percent again, because those typically cause full table scan and very inefficient. Now, we have covered single column indexes. So how do multiple column indexes work? Well, in this case, we essentially have 2 or more columns, right, which are almost like concatenated to create a tuple, and the sort order between those defined as the first column is compared to the second, then third, and so on and so forth. What is important in this case to understand is for multiple column indexes, it is still one B+Tree which is created, not any kind of fancy structure where it's separate B+Tree for each level or something like that. It's one B+Tree, just their comparison rule applied from the first column to the next in the index. Now, the other thing you need to know about the indexes is what indexes are not free. They're actually quite costly, so you don't want to add more indexes than you need for your application to work well. And typically, you are thinking first about the number of indexes and then about how many columns index has. So if you have a choice between adding another n index or extending existing one with another column, then extending is better in majority of the cases. Now, indexes have overhead both in reads and writes. It's very well understood for writes, right? Because updating the data often means updating indexes as well, and the more indexes we have, the more expensive it becomes, right? But it also makes reads more expensive, which are not optimized for those indexes, because wasted indexes means wasted space in disk and memory as well as additional overhead for MySQL Optimizer, which will have to go through all existing indexes in many cases and consider them for query execution. If you have those indexes, there will be more overhead. Now, when we speak about the cost of indexes, there are multiple things which impact that. Things, for example, like long primary key is rather expensive because it makes all secondary key longer because they contain primary key, right, to refer data for. Random primary key for Innodb is quite bad because it is a clustered key, and random insertions will contain a lot of page split and will result in a very fragmented and poorly performing table. And what I mean by random in this case, it does not necessarily have to be true random. If you have, let's say, a key of SHA1, right, or of something as a primary key, that would be a pretty bad choice because it spreads the data across all their order of the keys very uniformly. Now, having said this, long indexes are generally slower, right? So if you have index on varchar 255, right, the very long string, it will be longer and slower than the index on a couple of integers. Even when it's not just a primary key, but indexes with insertion and random order are more expensive, while indexes with sequential inserts, for example, which are correlated with your primary key values, can be cheap. For example, if you have after increment ID and then insert time, which grows essentially sequentially with after increment value, it wouldn't be very expensive index to keep. Also, again, for inserts, specifically low selectivity indexes such as index on gender or state, they are significantly less expensive than high selectivity indexes. Now, when we are using Innodb tables, then it also makes sense for us to take the most out of our primary key. We want to pick primary key which suits us best, keeping in mind what lookups on a primary key will be fastest for Innodb tables, especially for ranges. One of the very common tricks we've been using is when you have something like messages or comments for the post or something like that, it's very powerful to create primary key which contains post ID, something like post ID, comment ID. Why? Because that allows us to keep all the comments essentially clustered together or one or few Innodb pages which can be retrieved very quickly. In some frameworks, you may do much better having just single integer key. In those cases, you can just maintain keys to concatenate those values in a single large big columns, and that can be a good workaround. Another thing to consider is what in most recent MySQL versions, the primary key is implicitly appended to all the indexes. So if you have a primary key ID and then you have a key A, then the key internally will be as good as A, ID. And you can use that for sorting, for covering index, for lookups. So for example, key something like A equals to 5 and ID more than 100 can be resolved very well using just index on A. You don't have to have an index on A, ID. Now let's move on and talk about how MySQL really uses those indexes. And there are following ways. Data lookups is perhaps most important one. Sorting, avoiding reading the data, and some special optimizations as well. So how do we use indexes for data lookups? Well, let's look at this simple example. We do select from employees. We're looking by the last name. Having index on last name would help us to run this query in the most useful way. And then we can also have lookup on, let's say, last name and department. In this case, a combined index will allow for a query to run most efficiently, having index on department last name or last name department for this given query. Now let's see how indexes can be used if you have an index with multiple columns. Let's say we have index A, B, C, right, exactly in this column order, because column order matters a lot when you have indexes. This will essentially three variants, right? First of all is when index will be used for all listed key parts. And these are cases when you have a range on the first column, right, or equality on the first column and range on the second, things like this. You can see in these cases, index can be used for all columns. Even in the last mentioned case where you have A is equality, B is in the list of values, and C is a range. Now, it's worth to note that there is a second common case when MySQL will not be able to use the index. It is in the cases like B more than 5, because the leading column is not referenced in, and MySQL only can use the indexes starting from the first column and then adding other columns to the index use only if it's possible, right? But this is only, there is also a third case, which I believe is one of the more complicated, is when you have index used, but it's not really used to a fullest extent as you would expect. For example, you have index A more than 5 and B equals 2, you may see, oh, index is used and that's great, but in reality, only the key part of A more than 5 will be used for a lookup in this case, and then everything else will be post-filtered data. And in the second case, we have a similar situation. The first two key parts will be used, not all three, as we may expect. I believe this is a very important thing to know, because it's very easy to get a mistake here, thinking, oh, index is used, and not really think about what key parts are being used. Now, if you formulate that as a rule, I will put it this way: the MySQL will stop using key parts and multiple index as long as it meets any real range, right? However, if you have an in clause, then MySQL is still able to continue using 4 key parts. The second way MySQL can use index is use index for sorting, which can work in both cases. Like in this, when you do select from players, right, or what's not, and we can use index to sort the whole table, which is very important, because if you don't have an index to sort the data, you will see the file sort, which essentially have to read through all the table. It doesn't scale at all with larger data size. And we can also combine using index for lookup of the data and order by. So in the second case, we are pulling out the top scores for a given country called for US, right? And this can be sorted by index on country, score, where a key part country will be used for lookup, and a score to efficiently sort everything for this country. Now, when it comes to the sorting, it becomes even more tricky to see how indexes can be used for sorting. First is when you have multiple column index, you can sort by one column or 2 columns in the same order. You can also use equality search in the first column and order by second, again in both directions. Or you can have a range on the first column and sort by the same column. These all were situations where index, all the possible parts will be used. Now there is also a case where sorting will not be, index cannot be used for sorting. For example, we cannot sort by the second key part of the index. We cannot sort it by the first one. Like if you have key A, comma B, order by B won't work. We also want to be able to use the index if you have a range on the first key part and then the sort by the second key part. The index will be used for range sort, all right in this case, but you will have to do file sort for all the values which have A more than 5 in the given example, which is very expensive, right? It also doesn't work with in, right, contrary to their previous example with our normal lookups. And finally, you have to know that we cannot sort by 2 columns in the different order. We both have to, if there's multiple column index, you have to sort by in the same order. So again, following that out as a rules, you can see what you have to sort in the same order for 2 columns, and you can also use only equality comparison for all the columns in the index which are not part of an order by. Otherwise, MySQL will stop. I won't be able to use the index for an order by. Now, the next important optimization what MySQL has is its use the index to avoid reading the data. By the data, we refer to the data file if you happen to use MySQL tables, or primary key in case of Innodb tables. And we want to avoid doing that because that is an extra read, and also the data often is much larger than index and it doesn't present in the cache in the same extent. Let's see at the example. If you want to look up, for example, the status information for an order, for all orders for a given customer ID, right? You could possibly have a key on the customer ID alone, and lookup will be quite efficient. It will just find all the customer ID and then go to primary keys containing the information, right, about the order from this customer and fetch the status column. But it can be made substantially faster if you have a key on customer ID, comma, status, because in this case, MySQL will get all the data from an index alone, not going to the data, which is much faster, and it's especially valuable when we have access. We traverse many index entries this way, because access becomes more sequential and less random and jump into the different location in the data files. MySQL can also use index to optimize min and max aggregate functions. But note, only those 2 aggregate functions. You cannot optimize average or any other true aggregate function which actually need access to all the data. When you have an index, things like select max ID or from table, or even let's say max salary for in each department, that can be optimized for index in both cases. In the second case, you can even check that by using for very special extra information explain, which is called using index for group by. So we have spoke about using indexing in the single table queries. Well, and beyond those, we often use joins in the SQL. This is what SQL is good at, allowing us to join table with data with different tables. How does indexes work in this case? When we look at the joins, MySQL essentially uses the nested loops method for majority of the queries. It's kind of used a modified and optimized algorithm, but logically that is what it uses. So it picks one of the tables, let's assume cost in this case, and it scans that some way to find all the comments, and then it's for each of them it performs the lookup on the second tables and so on and so forth. Now, in this case, their best way to handle this query is to have the index on the posts table, so we can find all the posts with author equals people very efficiently, and then have an index on post ID in comments, so we can look up all comments for a given post. Okay. Now, a couple of things you have to consider here. First, for joins, it's very, very important to have your joins indexed, because if your joins are not indexed very well, then it's likely to be their bomb just waiting to blow up as a data size will increase, because things can get really bad really, really quickly. If you can't have a join queries which is using index as well, you may have to redesign and re-architect things, but don't leave them if you expect application of any significant size. The other thing what you have to consider is what you really only need to do the indexes in the directions of a lookup, right? So what I mean here is we are going to look up from the author table, in a sense, to a comments table by the post ID. So that means that is index which is needed. The index on posts.id is not necessarily needed in this case to optimize this query, even though we're still likely to have it as a primary key. In so many ways, I see people just see all the comments which we meet in the joins indexed in all tables, and that produces a lot of unnecessary indexes and also often extra hard work for MySQL optimizer to research all the combinations how tables can be joined. Now, starting with MySQL 5.0, MySQL can use multiple indexes for the same table. Well, that is what something we call index merge. But it is important to know there are two very similar looking but very different variants. One is when you have two, let's say, equality conditions with and within them. And in this case, MySQL may be able to use two indexes on A and B separately to optimize a query, but index on A, B, which combines and can be used to resolve both those very close from the same index, will be much better. Now, in our case, if you have an OR within those conditions, then you have to have two indexes on A and B, and using merge within those is as good as it gets for such query. And it's worth to note that in this case, if you have index A, B and a query like this index won't be used. It won't be used at all, so keep that in mind. Another interesting feature what MySQL provides called Prefix Index, which allows us to build an index on leftmost prefix of a column, which can be very helpful if we are doing a lot of prefix searches or even equality searches, and that leftmost prefix is selective enough. It also can be very helpful for blob and text columns, because if you want to index those, you must specify a prefix. It can't be indexed in entirety. Two questions which have prefix indexes are, first, it cannot be used as a covering index. So keep that into account. If you change some index to a prefix index, you will lose ability to use that as a covering index, and it should be worth it. And also, choosing the right prefix length becomes an important question. Now, for choosing prefix length, one common wisdom is what the prefix should be selective enough. Now, in this case, we have a table with about 2 million rows, and we can see we have a total about 1 million distinct titles in this table, and 960K of different titles with different prefixes of 20 characters, right, and about 600 something which have a first prefixes for distinct prefixes of 10 characters, right? And in this case, you can see, hey, the 20 characters is very good. Is almost as selective as a full thing, while it's probably such index will take half a space or even less. Though it's not really enough to check for that. You also better check for outliers. In this case, we can see there is not a lot of outliers, right? where most common prefixes and the most common titles are very close by, but that's not always the case. For example, if you be speaking about indexes cities, right, in the world or wherever, we can consider what having a prefix of the first 4 characters really pretty good, right, to provide us a good unique selectivity. And in average, that's really the case. But this is only if you don't think about some very common 4 characters prefixes, such as sun space and new space, as an example, right? There are a lot of cities which come to those categories, and this is why such prefix wouldn't be very helpful, because looking up for San Francisco, right, or San Fernando would have to scan through a lot of index entries which match it. Now, let's talk about MySQL 5.6 a bit. What exactly has changed out here, and what we should consider for index design? Well, the best thing here is what there are a lot of optimizer improvements in MySQL 5.6, but most of them don't really need you to do anything in terms of your index design structure. They will just apply the new query execution methods, which commonly can be based on the same index strategy as you had for previous MySQL version. One thing I would note, which has a very new meaning in MySQL 5.6, is the join buffer size variable. Previously, that was kind of a throwaway variable, which was only made sense when you're doing the joins if no indexes, and hey, who would do that? But in MySQL 5.6, it's also used for some of the new advanced optimizations, such as batch key access, and so setting it to higher values, something like 32 megabytes, often can make sense. Now, the most important thing I would think we should talk about for index design consideration is a new method of data access called index condition pushdown. So what is index condition pushdown, also called ICP? This is essentially where MySQL optimizer can push certain conditions, you can think about those as a part of where clause, back to storage engine to optimize and filter, instead of fetching the rows from storage engine and then doing the filtering on the SQL level. And what this ICP allows us is to really sort of much more flexible covering index than ever before. Now, before MySQL 5.5, we had sort of all or known approach to using the index for reading the data, right? Either we had a covering index, and in this case, all reference columns must be there, or in this case, index will be used only for lookup, and then rows will be fetched and conditions, other conditions examined. In the MySQL 5.6, it changed, and let's look at some silly examples here. So if you have something, a query like we select column A from table and we have a clause B equals 2 and C like certain full text search query, like pretty bad one. Now in 5.5 and below, we have essentially 2 approaches to the indexes here. One is kind of traditional. We can say, hey, we'll just index, put the index on B to resolve bill equals 2 clause, and then everything else will be checked after rows are fetched from a storage engine. Or we could create index B, C, and A, which will be covered index, which includes all the columns included in the query. We can use that in MySQL 5.6 as well, but we can also create an index on B and C, which can be very valuable. For example, if column A is some very long column. What can happen in this case is B will be handled as a normal index lookup. Then filtering C with a full text search will happen on the storage engine level before passing data back to MySQL. and then only rows which match both those conditions, which are few, right, will be passed back, so the A column can be fetched from a primary key. So another optimization can happen to the limitation of the index which I mentioned. Like if you have index A, B, and C, if you have index on A where A equals 5 and C equals to C only, then we say, hey, only first key part C equals 5 to be used, right? Well, right, but in MySQL 5.6, you will also use index condition pushdown, so only index entries will have to be examined for A equals 5 and filtered wherever C equals 6 or not all the rows, which can be significantly cheaper. Now the next question to talk about would be, how does MySQL Picks index to use? And it's good to note what MySQL really performs picking dynamically for every query execution. Even if you're using prepare statements, then depending on the data state and the exact constants you pass, the query plan may be different. MySQL Optimizer has essentially two ways to estimate the number of rows, matches, and pick the good plans. If it knows the actual constant for index lookups, it will go and perform the so-called index dive in the table to estimate number of rows possible. If that's not possible, which typically happens for the tables which are not the first table, in the join order, MySQL will use cardinality information instead. This is something which analyze table updates. Now, it's worth to note what the big variable what MySQL tries to optimize for is essentially number of rows it has to examine, but it's not really what it's used inside the code. There is much more to that. There is a lot of various heuristics which have been accumulated through years, right? Where MySQL, for example, will consider primary key being special. It understands their benefits of using current index, or the full stable scan is faster, and so on and so forth. And it's really hard to remember what exactly can impact MySQL decision, especially because it's different between different MySQL versions. So my advice would be to really check the plans that MySQL actually uses in production on your real data. Don't think you actually know what exactly how MySQL will execute different kind of queries. How do you do that? Well, you do that with explain. Explain is a very great tool which you need to use, but explain itself will take a presentation on its own to cover how to read what it gives. So I will just refer you to their the manual in this case here. Now let's talk a bit about the optimal indexing strategy for your application. What is important here is what you build index consider all, or at least the most performance critical queries in the application, not just one by one. We want all where clauses for and join clause indexes that is possible. If not possible, at least the most selective parts which eliminate the largest amount of rows from consideration. Generally, try expanding index, right, if you can, instead of creating your own. We have discussed it's cheaper. And also make sure to validate performance plans, performance impact, because you may have some unanticipated impact. For example, things become very slow because index became too large and doesn't fit the memory anymore. Let's give you an example. Let's say you have two queries that you have to optimize, right, which are shown on the slide. Now, if I would be looking at those queries one by one, looking at the query number one, I would build an index in A, B. Well, just because those or clauses happen to be written in this order, right? Now, if I look at two of those queries at the same time, I would put B and A index first because it covers both queries better. So I wouldn't create index on A comma B and then a separate index on B comma over K, right, if I look at. Now, if everything is being equal in terms of what kind of key parts you can cover, it's better to put the most selected key parts first, but it is less important than actually setting up MySQL can use them in a best possible way. Also note what you should not add the indexes for non-performance critical queries, because many indexes may slow the system down, and sometimes when you have some report which you are doing once a month, which, well, maybe taking a couple of hours, but that's good enough for you, it's not worth to optimize that at the cost of your everyday real-time queries. Finally, let me cover a couple of tricks which you can use to work around the MySQL optimizer limitation. The first one I called enumerating ranges. Let's say we have an index on A, comma B, and we have something like select where A between 2 and 4 and B equals to 5, right? As we discussed before, that will conventionally use only one part of an index, right? Because after between, no further key parts can be used. But if instead you will replace that workflow between with all the exact values which are in that range, like 2, 3, and 4 in this case, then MySQL will use both key parts. And yes, MySQL is not smart enough to do that by itself. You can actually extend this technique to add a fake filter. If you have some prefix column which is not very selective, like in this case the gender, and majority of your queries both specify, for example, gender and a city in this case, but you also would like to run the queries which don't specify the gender, well, then you can add their in clause which specifies all different values which could be in a gender column. Like in this case, for example, we talked about only the most popular genders out there. And this trick actually works with other things. It works with gender, status, Boolean types. It can also work with things even like states, for example, where there are not too many different variants, right, to put in. The third big limitation is dealing with a sort. As we spoke about, the sort optimization ability is quite limited, right? So if I have to have some where clause which is more than equality on my first column, then I will have to will get a file sort. In many cases, we need something like in. So we are, let's say, like in this example. What we can do in this case is we can rewrite this as instead of in, as a union all query, right? And in this case, if you take a look at this query plan, it will be nasty. You will see some much more nasty looking plan than for normal static. That query can often go many times faster than the original one. Well, that's it regarding presentation today, and Matt, now we're ready for questions.
Excellent, thanks, Peter. Got some great questions. Just as a reminder, if you have any questions, please post them here, and we'll get to them with Peter. So let's just start off with a question here with regard to covering indexes. They matter in where, group by, and order by clauses, but not the fields in select, right? does the order of the columns in the covering index matter, or do you have to use the first one somewhere in the query to be able to leverage the others in that covering or composite index? So I guess it's a two-part
Okay.
here.
So the question, as I understand, in which order do you want to use the columns for a covering index? So what we typically design here is first you want to put the columns which you're actually going to use for your lookups and file sort and the sorting, right, if there are such columns. And after those columns, you can append other columns in the any order, right? It doesn't matter in this case when you speak about one specific query. But remember, often you may have the same index which is used by some other queries. So I typically would see what kind of order of the columns may help benefit in some other queries which I either have right now or may have in the future, right, which could use those added columns for lookups or sort or something like that. So that is how I approach design for covering indexes.
Okay. This, I think, maybe relates to your second trick. So near the beginning of the presentation, you spoke about different types of indexes. This question is about the bitmap type index. And let's say that there are 5 or 10 different values in 1 million rows of data. And Oracle has the bitmap index, but MySQL, is B+Tree only available? Would it be too costly? And then I guess my follow-up is, would this be a good application of your second trick?
Yes, well, yes, I mean, this is right. MySQL at this point doesn't have the bitmap indexes. So there are multiple workarounds which you have to use, right, to alleviate those depending on exact conditions, right, and that's maybe one of them.
Okay. So when you were discussing the costs of indexes, a question came up. What do you mean when you say when you say extending index is better than adding a new one? Can you give an example?
Okay. So so the example is as follows, and I will use something which I use for this presentation. Let's say you have the query we just did. You have an index on just column A, and then you have a query which has a lookup on A, B, right? A equals to 5, B equals to 5. When you really have two choices, right? Just say, oh, this query needs index on A, B. Why don't I go ahead and create that, right? And in this case, in the end, you'll have index on A and index on A, B. While most likely extending the index A to making that index to be A, B would be better instead, right? And this is a very, very common problem I see with MySQL DBAs and developers, which don't look at what kind of existing indexes exist already, and just when they see query which is not running well, they just add a new index for that query.
Kind of as a follow-up to that, other than explain, can you recommend any other tools for index usage optimization?
Oh, well, I would say that the explain is a main tool. Now, in addition to that, I think it's very helpful to use their tools to observe a true query performance. So you can use tools like PT Query Digest or our toolset there, Percona Cloud tools, where you can essentially see at the query execution time before and after you implemented the change, which can be very valuable because it allows you to see in the production not only the impact to the query you are trying to optimize, but to other queries as well. Because you may have sometimes unexpected side effects, right? You optimize this given query, but your insert started to be a lot slower, or you have triggered some bug and some of the other queries start to be getting bad optimizer plan and so on and so forth. There's a lot of possibilities here.
All right. There was a slide, 2 slides before the multi-column index page where you had an example, and if the attendees wondering if you could elaborate a little bit on the example. I don't have the slide number, but it's 2 before the multi-column indexes page.
Yeah, well, let us take that for a blog post, right? I don't think it's easy to elaborate on the question this way.
What is the rule of thumb for setting the value for join buffer size for systems with, say, over 16 gigs of RAM?
Oh, for join buffer size?
Join buffer size, yeah. Are there any best practices?
Yes, well, yeah, I mean, it's very tricky to say that in this case. The thing here is it's not just a question about the amount of RAM, but that also about how many queries you run concurrently and how much data it goes through, right? So when I speak about batch key access, what it gives us is it optimizes access by sorting keys and accessing them in their more sequential order. So if you have a query which accesses, for example, 1 million of rows, then that means it will have a chance to sort those keys to access in that order, and this means it may be able to use up to 16 or 32 megabytes of memory, and not more, right? So the 2 factors you have to consider first: how many keys, how many rows that query can access, and so how large join buffer size it could possibly use. And the rest, second, is how many queries are you planning to run concurrently, right? Because if you have a lot of those queries going in parallel, then you have to account on having enough memory to allocate that join buffer size for all of them, as well as have enough memory for energy buffer pool and what's not.
Okay, okay. And I think we have time for one more question. What are the positives and negatives, or just overall considerations, when indexing a varchar or a text column? In general, when is it a good idea to do, and when is it a bad idea to do when you're balancing performance and disk space? And are those the primary concerns?
Well, interesting question. Well, the thing here is, if you need a query which looks at a large amount of data to run faster, and the very close happens to be varchar, then it has to be indexed, right? And their storage impact often becomes a secondary concern, which can be dealt with in different ways. We can, for example, choose not to create a full index, but only create a partial index, prefix index for varchar. We can also choose things like enable Innodb compression if we need to store a data space, or even use a different storage engine such as TokuDB, which can allow us to fit much more data in the same storage size. So that would be an answer.
Okay, excellent. If anyone has any more questions, please post them here. We will get to the rest of the questions, quite a lot of questions, with a follow-up blog post. And with that, I'll hand it off to Elisa. Thanks, Peter.
Thank you, Matt and Peter. Great job today. Peter, there are tons of questions, and just like Matt said, I will make sure that Peter has every last one of the questions in his hands to address in a follow-up blog post. Thank you, everyone, for joining us today, and next week we hope that you join us on May 7th for a webinar on 9 Percona toolkit tools that you can't live without. Love to see you there. And with that said, thank you very much for your time today, and we hope to see you in the future. Take care, everybody.